Okay, thanks for the nice introduction and the invitation. So this is my overview of my talk. This mostly follows the SNOMA's white paper on the physics reach at Belle II, and I will be focusing on this section of the tau physics. And the topics that are highlighted are the Lepton Flavor universality, Cabibbo angle anomaly, charge Lepton Flavor violation, and the electric and dipole moments of the tau, and the second class currents. So let me start with a very general outline about the tau decays. So the tau decays tau is the only lepton heavy enough to decay into quarks and leptons, and it decays primarily into the UD bar, where the D bar is this mixed state between the Cabibbo suppressed and the Cabibbo allowed final states. This diagram here shows the breakdown of the naive expectation and how they compare. So the naive expectation is about 20%, 20%, and 60% should be the leptons. And 60% should be the quarks. However, there are QECD and QED corrections, which change the 60% to the 61%, and the leptonic parts to 17% about. So after these corrections, we have these branching fractions for the different exclusive states, as are shown in this diagram below, and excerpts from the branching fraction listing from the PDG. So let me move on with the lepton universality first. So firstly, looking at this ratio of this diagram from tau to muon divided by tau to electron, we can get the ratio of the coupling between the muon and the electron from this. And we can measure this ratio, and from that, the square of it gives the G mu over GE square. From the ratio of tau to muon, and muon goes to electron, which is almost 100%, we can see that in this ratio, the G mu will cancel, and the ratio is sensitive to G tau over GE. And looking at this expression, we see the quantities that we need to measure for extracting this quantity is mu, the mass of the tau, the lifetime of the tau, and the branching fraction of tau goes to muons. Similarly, from the ratio of tau goes to electron and the muon, which decays almost 100% into electron, we see that the GE part cancels out, and the ratio is sensitive to the G tau over G mu. So in this case, we need to again measure the mass of the tau, the lifetime of the tau, and the tau branching fraction into electrons. And from this, we can extract the coupling constants ratio of G tau over G mu. Now, G tau over G mu can also be obtained by looking at this diagrams, which is showing tau goes to, for example, pion, and pi goes to mu. In this case, the coupling, the yellow vertex that is shown here is again G tau over G mu, and the decay constants for the pion cancel in this ratio. So in this case, we need to measure again the mass of the tau, the lifetime of the tau, and the branching fraction of tau goes to pion, or tau goes to kaon, because both of them are sensitive to this ratio. We typically don't use the electron decay of the pion or the kaon in this way, because those are helicity suppressed and therefore have larger errors. Because we like to make a precision measurement, that's why we use this G tau over G mu to extract the ratio from the leptonic as well as the hadronic decays of the tau. So the H-FLAV combination is presented here. So from these quantities, from the current knowledge of the different quantities I just now mentioned, we can measure the G mu over GE up to a 0.14% precision. And similarly for G tau over GE. For the G tau over G mu, we can average the quantities that we obtain from the tau leptonic decay and from the pion and the kaon decays. And we again obtain a precision which is similar of the order of 0.14%, and the correlation matrix from the different quantities are shown here. So these are the newest number from the HFLAV combination. To give you the summary of the measurements that we have used for the G tau and the M tau and the lifetime of the tau. This page shows the current state. So the measurement for the mass of the tau is dominated by the measurements near the tau threshold, and that has reached an error of the order of 0.12 MeV, which is really quite precise. For the lifetime, the most precise number comes from the measurement of at Belle, which used 3 versus 3 topology. And in this case, precision of the order of 0.5 femtoseconds has been reached. Next page shows how a tau pair event looks like at Belle. This is a very characteristic signature of a tau pair event, going into an electron on one side and 3 pions on the other side. This is kind of event is conventionally called 1 versus 3 topology, and you can see the horizontal, the side view as well as the view down the beam pipe for these different for this event. And this is how a characteristic 1 versus 3 looks like at Belle 2. The tau mass measurement can be improved, and this is an ongoing study at Belle 2. The method that is being used is to calculate the so-called the pseudo mass variable. Here we use 1 versus 3 events. So the 3 pions are the signal side, and we try to measure the mass of the tau by looking at its behavior near the threshold. So the pseudo mass defined variable is defined by approximating the neutrino direction to be collinear, and the turn on curve here is a measure of the tau mass. So from this quantity, the tau mass can be measured from the cutoff. And the present status of the measurement with only about 8 femtobarn inverse of data at Belle 2 is shown here. This gives a statistical precision of 0.75 MeV and a systematic of 0.33 MeV. The statistical precision is already improved by the current state of the data taking, which has now 360 femtobarn inverse of data. So that is almost comparable to the world precision. However, our present study is still limited by the systematic error, which is around 0.33 MeV. Several ongoing studies are aiming to reduce this systematic errors, and we hope to bring it down towards the world precision, and that is one of the important goals of the high luminosity Belle 2 data. Next, I show the tau lifetime measurement and the prospects. So the present measurement, the best measurement comes from the Belle experiment, where we look at 3 versus 3 topology. And the error is around, statistical error is 0.5 femtosecond, and the systematic error is 0.33 femtoseconds. At Belle 2, we are planning to update this measurement using 1 versus 3 topology events, thanks to the excellent improvement in the vertex detector at Belle 2. So this is shown here how the 3-prong can be extrapolated to the interaction point, and from the measurement of this decay length, we can extract the lifetime information. Next page shows the comparison between the resolution from the improved vertex detector at Belle 2 versus the one at Belle. A factor of 2 improvement is expected, and that is shown here on the plot on the left. And the measurement is actually the lifetime is obtained by fitting this proper time distribution after subtracting all the backgrounds. and the current measurement gives a statistical error of 0.5 femtosecond with about 200 femto1 inverse of data. So this is quite interesting because we have already managed to reach the statistical precision of the previous best measurement using 711 femto1 inverse of data. And the systematic studies are ongoing, which aims to reduce the extraction to the previous level or even better. Next, I show the interesting part of why we want to study the Lepton Flavor universality at Belle II. There are some unique features that can be only accessed at the E plus E minus collisions rather than other place. Namely, we can have a contribution to the Lepton Flavor universality from a Z prime. And the same Z prime can also contribute towards the anomalous magnetic moment of the mu, as shown here. So these are the different limits that we can obtain by constraining the ratio of the couplings at Belle II to about 0.1% error. And these red curves show how the limits on the different couplings of this Z prime looks like. And this is quite unique to the E plus E minus machines. So we plan to measure this ratio of mu over E, and the goal is to include both the 3-prong as well as 1-prong events. And the precision on this Lepton Flavor universality will be significantly improved by this measurement from the high luminosity data at Belle II. And this will give some of the most stringent constraints on the non-standard model deviations from the universality. Next, I will move on to the CKM measurement of the VUS from tau decays. So to introduce the CKM matrix, the VUS is the largest off-diagonal element. And from the first row, we can obtain this constraint, namely the VUD square plus VUS square plus VUB square equal to 1. The VUB plays a very minor role in this equation. The precision that is obtained from the VUD is around 0.0031, and this directly translates into the error on the VUS obtained from the CKM universality. And the expectation is that we have about 0.2277 value for the VUS. So this is a precision test because the errors are already quite small. So, however, we can have a violation of this equation by having a term that deviates from 1, and this is proportional to the new physics, given that can come into the loops as shown in these diagrams. So we can have Z prime or leptoquarks or charged Higgs that contribute to this deviation of this delta, and that will show up in a large class of models, and that will be specifically interesting in the tau decays. So these are the different approaches to the VUS. We can measure VUS from the 3-body decays of the kaon or 2-body decays of the kaon, or from hyperon decays, as well as from the VUS decays. In all cases, this vertex shown here in red is the one that is sensitive to the VUS, and the quantities that are extracted are, in addition to VUS, the meson constants or the form factors, which are usually either calculated from the perturbative fusity in the case of tau decays, or obtained from the lattice. So here is how the calculation for the extraction of VUS from tau decays proceeds. We look at the R quantity, which is defined as the ratio of the lifetimes for the tau decaying into hadrons normalized to the tau decaying into electron, which according to the naive expectation should be around 3. However, we have QCD and QED corrections, which make it different from 3. These corrections can be broken up into the SU3 conserving part and the SU3 breaking part, and these are then proportional to the VUD square and the VUS square respectively. So the equation that we use to obtain the VUS is then given by this flavor breaking term, this correction term. The quantity that we want to measure is R tau and the different spectral moments of this R quantity. The KL moment is defined in this equation here by weighting the invariant mass distribution by integers K and L respectively. So the 0th order moment refers to the branching fraction. And the correction for the SU3 breaking term is presented here. Using the latest corrections, we get about 0.238 plus minus 0.033 as the delta R correction. And then using this delta R, we can measure the VUS by measuring the R strange and the R non-strange. We can also use some weights which are obtained from lattice as an alternative, and that gives a similar equation that can be used to obtain the VUS from tau decays. So here is how the measurement proceeds. We average all the measured strange branching fractions and in the H flag, and from that we obtain this quantity, the strange branching fraction, inclusive of all different final states. And then we also measure the by averaging all the measured quantities, known measured quantities. To obtain R, we normalize these branching fractions with the electron branching fraction, and we improve the precision on the electron. Namely, we use the measurements of the mass and the lifetime to obtain a better quantity, better error on the electronic branching fraction. So by putting these all together in this equation here, we obtain the VUS from tau decays from the inclusive, which has an error of 0.0021, out of which 0.0011 comes from the delta R theory breaking term, this term. Of course, the dominant error is coming from the experimental measurement of the strange branching fractions. We can also measure VUS from the exclusive tau decays by looking at either the ratio of tau to k divided by tau to pi or to tau to k alone. And the various correction factors from the QCD thankfully cancels in this ratio. We have some long distance large effects, small effects, which are expressed as 1 plus delta R term. And also we use the, in this extraction, we use this ratio of Fk over F pi from the lattice, which are obtained from the 2019 flag averages. So putting this all together, we have the different measurements of VUS. So firstly is the measurement of VUS from the KL3 decays, which interestingly differs from the unitarity by -3 sigma. Similarly, the K-on decays, KL2 decays also differs from the unitarity by about 3 sigma. The inclusive measurement differs from unitarity by about 3.7 sigma. The VUS from the ratio of the tau to k over tau to pi falls short of unitarity by about 2.1 sigma. The one that is measured from the tau to k alone falls short of the unitarity by 2.6 sigma. In the average, we find the whole extraction of VUS from tau decays is 3.5 sigma less than the unitarity. So this is quite interesting and is called the Cabibbo angle anomaly, that both from the kaons as well as from the taus, the VUS extracted is less than unitarity by about 3 sigma. So taus here actually have a very unique role, because the extraction from the inclusive tau decay is using a different kind of theoretical calculation than used in the kaon decays, which relies on lattice error. And of course, the new physics that are only affecting the third generation will be providing corrections to the VUS from taus. So the tau decays at Belle II thus offers very unique and complementarity insight into the Cavive angle anomaly. Next, I will move on to the subject of lepton flavor and lepton number violation. So lepton number and lepton flavor are not forbidden by any continuous symmetry, and the most new physics models naturally include it. In the standard model, we can actually have lepton flavor violation in the charge sector coming from the neutrino mixing. However, the order of magnitude estimate gives a number of the order of 10 to the power minus 54, which is several times below any experimental sensitivity. Thus, if we do find any hint of lepton flavor violation, we can conclude it is an unambiguous signature of new physics. And of course, mass-dependent couplings are expected to enhance this kind of predictions, which in different models have different values, which are almost close to the experimental bounds. And in different models, we can either have the predictions of tau to electron transition or tau to muon transition as a dominant decay. So because of this model independence, it is critical to look into all different final states as possible and both the leptons. So the neutrino-less two-body decays and the three-body decays are signature of this lepton flavor violating signature, and we can have different models predicting of the order of 10 to the power minus 8 or 10 to the power minus 10. Also, different models gives very specific prediction of the ratios of, for example, tau to mu eta or tau to mu gamma or tau to 3 muon. Thus, measuring all different final states provides a test of which model is causing the lepton flavor violation, if at all. Here are different contributions shown at the tree level for tau to electron transition. And also in the bottom row, we have the contributions of new physics shown at the loop level. And all of these are expected to be present at bounds just a little less than the current experimental bounds, which makes all these searches very compelling. In the E plus E minus collisions, we have a very clean initial environment because our initial state is leptons and are quite well known. And also we have the beam energy constraint. This makes the searches very efficient in at Belle II. Here are shown how we can look at the topology between, say, tau to lepton and a photon, or tau to 3 leptons. In the case of a tau to lepton, we will have in the signal side 1 lepton. And in the case of the 3 leptons, we will have 3 leptons on the signal side. Or we can also have lepton hadron hadron in the final state. In case of the tau to E gamma or tau to mu gamma, the principal background comes from radiative Bhabha or dimuon. And also we can have some irreducible background from the tau decays. The QQ bar typically plays a small role, a small contribution in this as a background. In the case of the 3 leptons, we again have contributions from the Bhabha or the dimuon events, and also from the miss ID from the QQ bar events. One of the most interesting characteristic that is typically used to differentiate between signals and background are the number of neutrinos in the signal side and the number of neutrinos on the tag side. So for the signal events, we will have 0 neutrinos on the signal side, and in the tag side, 1 or 2 neutrinos. And in the case of the tau pair background, we will have 1 or 2 neutrinos on both sides. Whereas in case of Bhabha and QQ bar dimuon events, we will have no neutrinos. So this difference helps us to separate between the different backgrounds and also differentiate between the signal and the background. So here is how we make the most interesting discriminating variable. The two most interesting discriminating variables are the beam energy constraint mass of the system of the daughters of the tau. In this case, for example, if we look at a lepton gamma system, then this is the equation for the MBC variable. And the delta E variable is the difference between the energy of the daughters of the taus and the beam energy. And we expect the mass to be clustering around the mass of the tau and delta E to be clustering around 0. So on a two-dimensional plane, the signal should appear in this green ellipse shown here in this diagram, or in this magenta ellipse shown in this search from Bell and Barber respectively. So the Barber search is shown for the tau to E gamma, and the Bell's result is shown for the tau to mu gamma. And the signal region is shown here as ellipse. Then, since we have not found any event as yet, we estimate the upper limit. The upper limit on the branching fraction is calculated using this master formula, which has in the numerator the number of signal events at the 90% confidence level, and in the denominator the product of the number of taus and the efficiency. The efficiencies are typically estimated using signal Monte Carlo, and have different factors, namely about 90% comes from the trigger, 70% reduction comes from the reconstruction of the final state, and the topology of the event can cause another reduction of 70%. Particle identification cuts have efficiency of 50%, and similarly we can have cuts and the signal box, which typically give a efficiency of the order of 5%, between say 2 and 10% roughly for the different searches. Here are the summary shown for the Barber search for tau to E gamma and mu gamma, and the Bell search on tau to 3 leptons. Upper limits of the order of 10 to the power minus 8 are obtained in these searches. And the biggest scale factor is coming from the number of taus that goes into the denominator of this calculation that sets the scale. In the Bell case, we used 1438 million events, and in the Barber case, about 1,000 million events. So this is how we obtain an upper limit of the order of 10 to the power minus 8. Here I show different upper limits, how it has progressed from over the different several years from the different experiments for the tau to mu gamma final state, tau to mu eta final state, tau to mu final state. And we can see over the period of the last 40 years, we have reduced the sensitivity of the lepton flavor violation from around the percent level down to 10 to the power minus 8 level. And the different predictions from the different models are shown here, which are around 10 to the power minus 8, 10 to the power minus 10. For the future prospect, we can look at all the final states that are possible and divide the searches into two types. The tau to E gamma, tau to mu gamma are background limited searches. So in this case, the numerator of the formula, the number of 90% upper limit and the number of signal events, scale as the luminosity, as the square root of the luminosity. And because there is already a factor of luminosity in the denominator, the branching fraction will scale as 1 over root of luminosity. In case of the background free searches, and most of the other searches here, other than the tau to E gamma, mu gamma, are assumed to be background free searches, since we have not yet observed any significant expected background yet. So for this, the number of the signal N90 is taken to be 2.44, which corresponds to the Fieldman-Cousins approach for the number of observed events equal to 0. And this corresponds to a scaling which is directly proportional to 1 over L. So different scenarios for the upper limits at Belle using 5 fem-to-1 inverse of data and 50 fem-to-1 inverse of data are shown in this diagram. And upper limits of the order of 10 to the power minus 9 to 10 to the minus 10 can be reached with the full data set at Belle 2. It's quite interesting to look into the model independent probes of new physics by looking at the Wilson coefficients, the Cn, at different scales. So this plot shows how the different measurements from IISc, LHC, and Belle and other experiments compare. In the case of the tau2 electron transitions are shown on the left, and tau2 muon transitions are shown on the right. The scale here is that as you go down in the scale, the lambda scale is increasing. So and also the coupling is decreasing as you go down in the left plot. So this is how we can compare the different sensitivities using high luminosity projections of Belle data. The Belle and the Belle 2 limits are also compared for the tau to mu transitions on the right of the diagram. And here we can compare from the different final states and the different Wilson coefficients. And we can see that we can reach sensitivity of the order of UTeV in the scale of new physics from these searches. Next, I will move on to the discussion of the electric dipole moment. So the electric dipole moment is essentially a measure of the charge asymmetry. And we can conveniently take the spin direction of the lepton to be the axis around which the charge asymmetry is studied. So the electric dipole moment is coming from a CP violating term. So if we look into this tau gamma vertex, so we are really probing the CP violating contribution by studying the electric dipole moment in this case. The standard model prediction is of the order of 10 to the power minus 37, which is of course far below any experimental sensitivity, but new physics contribution could enhance this effect to of the order of 10 to the power minus 19. Again, if we do see a non-zero electric dipole moment, it will be an unambiguous signature of new physics. So it is quite exciting to search for it. The current status of the electric dipole moment is shown here for the different experiments. For the Belle data that using 833 fem-to-1 inverse of data, we obtained upper limits on this D, the electric dipole moment term, the real and the imaginary parts, and the upper limits are of the order of 10 to the power few parts in 10 to the power minus 17. So this is consistent with a zero EDM. The statistical and the systematic errors are similar. The dominant systematic error comes from the disagreement between data and Monte Carlo in the momentum and the angular distributions. For the future projection, we expect Belle 2 to be able to perform much better. So preliminary studies have been performed at Belle 2, and we have been able to have a much better control on this leading systematic error. So the leading systematic error can be significantly reduced almost to the level of the statistical precision of the search. And thus we make a extrapolation based on the statistical error, and we expect to be able to probe to 10 to the power minus 19 with 50 auto 1 inverse of data. There is a very interesting proposal to upgrade the Super KK collider with polarized electron beams, and that will also provide further improvement in the sensitivity in the electric dipole moment. Next, I will discuss the magnetic dipole moment. The different measurements summary of the measurements of the magnetic dipole moments of the electron, muon, and the tau are shown here. The standard model predictions is quite small, is of the order of 10 to the power minus 4. Since the tension has already been seen in the G minus 2 of the mu, it becomes exciting to search for the G minus 2 in the tau. The current bound is of the order of 10 to the power minus 2 coming from the Delphi experiment back in 2004. There is also another measurement from Atlas that is looking into the lead-lead collision that was presented earlier this month. And it also has a similar sensitivity of the order of 10 to the power minus 2. Belle II will be able to improve upon this sensitivity quite significantly, and also with polarized beam. So this is the framework in which we study the magnetic moments. We look at the effective field theory parameterization of the gamma, which has this radiative correction as an F1 term. The F2 term is the one that describes the magnetic moment, and the F3 term is the one that describes the electric moment. So here we are trying to measure the F2 term. The procedure to measure this is shown in this very complex set of equations. So we can measure the transverse asymmetry, which is parameterized by A tau, and we can measure this longitudinal asymmetry, which is parameterized by AL. And then we can combine these measurements of the transverse and longitudinal asymmetry to extract F2. The contributions of F2, the standard model expectation at 0 and 10 GeV square is shown in this table. And the units of this are 10 to the power minus 6. Given the fact that most of the systematics will cancel when we try to measure this kind of asymmetry, with 40 Autobahn inverse of polarized beam data, we expect to obtain a precision of the order of 10 to the power minus 5 or even better. Finally, I will discuss the second class current. The hadronic current in the tau decays is shown here, which has contributions from the vector as well as the axial currents. The G parity, which combines the effects of charge conjugation and the isospin rotation, is shown here. And the dominant terms are shown by this classification of the G parity versus the axial and the vector currents. The dominant term is the leading allowed term, which is called the first class current. And the second class current is the one that is shown in the last page. This was predicted as early in 1958 by Weinberg as the second class current to be highly suppressed in the standard model. In fact, it is suppressed at the level of isospin breaking, which is proportional to the difference between the U quark and the D quark mass. And hence, in this tau to eta pi decay, we expect the standard model contribution to show up at the level of 10 to the power minus 5. However, it can be further enhanced by several new physics contributions. For example, as shown here, from the charged Higgs exchange or leptoquark exchange. The Belle II projection for the errors on the branching fraction for tau to eta pi are shown here, along with the statistical and systematic contributions. And the significance is shown here in the high luminosity environment at Belle II. With about 20 Autobahn inverse, we expect to reach a significance, a combined significance of about 5 sigma for tau to eta pi. So it is interesting to note that the precision measurement of this kind of final state and associated with an improvement in the knowledge of the scalar form factor will be able to put very stringent bounds on the charge Higgs exchange, even if we do not find any excess from the standard model prediction for the second class current. And that is all I had to say. Thank you.
Thank you very much, Swagato. So, any questions
or comments?
Maybe while people are thinking, I had one question about these the Lepton Flavor violating modes where you had the ATA. Forget the page number. Here. So is this also looked for with the phi as well, or is that disfavored for some reason to look for?
No, there are predictions for all the different mesons. I just happen to be highlighting eta, which is
okay.
For which. So yeah, it is. There are predictions which are actually very model dependent. So it is useful to look into all different final states.
Okay. Okay.
So that is why in this table we do have the phi somewhere there.
Okay. Sorry, it's a bit small on my screen, so I.
Yes.
Notice. Okay.
Yeah. So we have expectation from all different. And
well, maybe as no one else, I had one question about this, the anomalous magnetic moment of the tau. Yeah, you mentioned in your slides, well, I think verbally about this stuff in that Atlas has done with its ultra peripheral collisions.
Yeah, it just came out earlier this month.
So just in comparison, how will Belle II, particularly with polarization, will that always be able to beat these kind of measurements at the LHC?
The LHC expectation is actually of the order of the same as Delphi, so 10 to the power minus 2. So we expect to be able to measure it down to 10 to the power minus 5.
Okay.
So currently, the Delphi or the Atlas measurement is barely able to reach the Schwinger term. But the goal is to be able to reach search for new physics at the 10 to the power minus 5 level, or 10 to the minus 6 level.
Okay, so I know, but also just extrapolating forward from the LHC, they would need a lot more heavy ion running than they're probably going to have to reach this level of precision, and the systematic will probably be very hard. Okay.
Yeah, that is one thing. The other thing important is that in the case of Belle II, because we are measuring asymmetries, several of the systematics do cancel. So that is one of the most interesting methods that we are encoding by looking at the combined transverse asymmetry as well as the longitudinal asymmetry and conjuring up this equation. So the precision of this is really very small. So we can almost scale down with the statistical number of taus produced.
Okay. Thank you, Swagato. So